So here's the deal, Ava. Rihanna's letting you down. I am recording currently, but we've already moved past the questions and we're covering the notes for the next chapter. So 100% Rihanna's fault, nobody else. So she's the one to throw under the bus. All right, here we go. New chapter. So we just got done talking about this. So hopefully it's refreshing your mind. What is total? What is internal energy? I mean, I know you see that definition there. That's not what I'm not asking you to say that definition. Please don't say that definition. It's what is internal energy? Yeah, basically the total kinetic energy of all the molecules. One thing you can remember that I potentially, it's ways back, when we first started talking energy, okay, let's do this real fast. When we first started talking energy, I made this giant energy tree in front of you. If you remember, I split between it was mechanical and non-mechanical, and out of mechanical it went kinetic and potential, and out of potential it went potential of gravity and potential elastic, and over here in non-mechanical we had chemical, nuclear, we had light and sound, and then we had thermal and electrical. Now, the reason I highlight this is one of the comments that I made back then is that in truth, all energies are really just kinetic and potential. That's it. That is it. That's all that is really up here. There are not 12 different types. There are 2, and that's it. Keep in mind that when you go very low, we give a different name to it, but it's really just this. So to say something has what is its total internal energy is basically, if I could take every single molecule in this room and do the 1/2 mv squared, then I could calculate that kinetic energy, and I would just need to do that for, simple task, every single molecule in the room, add that all up, and that would be total internal energy. The question, of course, becomes, the question that was set actually at the beginning of last chapter is, hey, Spainhour, I touch this desk, and I touch a piece of metal, and the piece of metal feels colder. When in all actuality, if you think about conceptually what temperature is, should those two things be different temperatures? Why or why not? They are not actually different temperatures. Why not, given the definition of temperature? So if, let's say theoretically that piece of metal, not theoretically, actually, that piece of metal that's sitting there, is it running into the air out here? Yeah. So if the air out here was, say, 25 degrees and it was colder at 23, then in generally speaking, they would be moving slower and this would be moving faster, and what would happen to that piece of metal? It would speed up. And when would it stop speeding up? In other words, when they are all the same temperature. So it is a fair assumption to say that every single object in this room in contact with air, albeit it doesn't have an external energy hitting it, should be the same temperature. There are several things that are not the same temperature as this room, though. What are they? Us. Correct. Why are we not the temperature of this room?
Because we have to regulate all of our body functions, and we have
fancy $10 word that we'll talk a lot more about, homeostasis. Right? Why do we have to go at 98.6 degrees? Or, like I said, females tend to be a little bit of degrees colder than everybody. Here is actually a smattering within that particular range. We're not all perfectly that, it's an average. Okay? Why is that the case? Because essentially, just real quick, sorry, going back to biology super fast, C6H12O6 plus a little bit of oxygen, specifically 6 of them, yields 6O2 plus 6H2O, if I remember correctly, if I'm doing my math. Dumb? No, that's right. Okay? So, that is known as cellular respiration. That is the fundamental equation at the very heart of absolutely every living human being, but also just living being in general. We take our sugar, we convert it over to ATP, adenine triphosphate. We break that third bond, put it in adenine diphosphate, and that bond is then carried out to basically do every single bit of work and energy in your system. As I am vibrating my diaphragm right now, that process is happening in there. But in addition to that, obviously my heart is beating and thus using that. My brain is hopefully relatively working right now. On top of that, my muscles are going back and forth all the time, moving all over the place because I talk with my hands, blah, 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 and I'm moving around from place to place. On top of the fact that you have a bunch of different processes like Your bones are building particular bloods, and proteins are being made all over the sorts of your body. And all of these things require energy, and that energy runs on this guy right here. Now, do you want your body to not be able to regulate this process? Why would it be terrible if your body just did this as fast as possible? Well, you'd burn it all up. You wouldn't be able to use it. You wouldn't be able to store it. You wouldn't be able to control it. And that process would happen so fast and so hard that it would cause a lot of extra energy. And going back to this conversation, where does extra energy always end up? Thermal. And of course, that goes back to the initial situation that if we were burning it like crazy, the temperature would go up. Now, the problem with the temperature is the average movement of kinetic energy. So what you kind of want to think about is a conversation all the way back in biology. My apologies for this, okay? That this process actually kind of needs a little bit of an activation energy. Okay, it needs a little boost to get over the hill and give it that little. That's how we control this process. Where this hill starts is your internal temperature. So why do we regulate at 98.6? Because we want to regulate that process to run the rest of your body. What happens if your temperature gets too low? Your cells cannot freaking work because they can't pull off cellular respiration anymore. You're dead. That's why being colder is vastly worse than being hotter. Hotter is still really bad. Why would it be bad to run a fever of 103 or 105?
Because you're gonna.
It is so easy to use that process that you potentially can spiral out of control using a bunch of extra energy and making that temperature go higher and higher. And if you go up here, you are definitely dead. Because now that's burning so fast in there that is not only creating extra heat to cause this process to go faster, but all that extra energy in your body is burning your cells alive, and obviously that wouldn't be great either. So we need to regulate at 98.6 degrees. So that's why you have to run. And how do they regulate that process? It's kind of simple. We kind of already talked about it. In general, homeostasis is all of your cells kind of deciding how much they do this. Right? And they can do that through a variety of processes. Let's say your internal temperature is getting cold. Well, if you're not wearing kind of any particular warm clothing, you're just wearing like a shirt and shorts and you're out in the cold weather, what simple thing does your body do in order to burn more energy? Shivers. It does that for two reasons. One, the process of actually moving your muscles will burn this energy and cause extra, but obviously two, the internal friction created by your body going back and forth will continue on that process as well. So, there you go, homeostasis in a nutshell. But internal energy, which has more internal energy? Okay, let's go simple here. I had that. Don't know why I had to do that. All right. This is the exact same temperature as this. Which has more internal energy? It's easy. What's this? Why?
Because
More.
it's denser and it has more.
There's something more. There's more than that. Yes, it's also denser. Now, I touched the two of them together. Okay? Will there be any transfer of energy between the two? This has more energy. Will there be any transfer of energy between the two of them? No. Why not? This has more. They're the same temperature, they're the same average kinetic energy, and therefore they are the exact same speed. Now, I touch this piece of metal. Will there be a change in temperature?
Yeah.
100% there will. I touch this. Will there be a change in temperature? 100% there will. Which way is it going to go?
You're going to make the ball hotter.
Okay, so simply put, which one of these experiences would you expect to happen faster and why? For the same amount of time, let's say that differently, for the exact same amount of time, which one would you expect more energy transfer between the two of these? Why?
Because there's less molecules that you're fighting. There's more molecules that
Going down, I would say that's probably my best. A lot of these were good and really close. I would say that's the best one, but simply put, these molecules move around very freely, right? They bounce around kind of all over the place. These don't bounce around very much. Okay, they're kind of held in place. Yes, they're vibrating back and forth at the same speed, but they are held on way more than this guy is right here. So in other words, like these molecules are the same speed, but as these guys like say speed up, they're bouncing away. So now the temperature in here has gone back to cold, you see? So they're gonna move around quicker, so this will transfer more energy in the same amount of time. So in other words, which one's pulling more energy out of me? This one, which means this one's going to feel colder, despite the fact that these two things are the exact same temperature. Yes?
They still like transfer energy, right? It just
100%.
like net zero.
If I touch these two, oh, right, yes, thank you, that's a good point. Yes, essentially you can think of it, as we've said before, kind of like this colliding thing. So yes, they are going over top of each other. I've got bad news for you in case you didn't think this was happening. If you touch anything, your atoms are going into that thing, its atoms are coming into you all the time, and probably on the orders of millions or trillions. That being said, when you really play out how many atoms you have, that is such a stupid small fraction that we would never feel like that is the case. Get a material that obviously holds on to you better, something sticky, obviously more transfer of material is going to happen, and if you get too much, then you like rip skin and all that sort of fun jazz as well. But yes, this is the difference between internal energy and heat. Internal energy is the total amount of energy I described before. And actually, let's go temperature here. The three things we need to know. Internal energy. Which of the three of us probably has the most internal energy?
You.
Me, for two reasons. What are the two reasons?
You have more.
I have more mass,
and
and I have a larger temperature, which means I have a higher average, right? Between the two of them, they are the same temperature, but obviously that has more because more mass. Does total internal energy have any impact whatsoever, though, on whether or not there is a transfer of energy between two things? No, not at all. There is no transfer between these two because they are the same temperature, roughly going the same kinetic energy, so as they hit across each other, they are the... So like, if you were the tennis ball, would you feel any difference of temperature touching the metal? No. Okay? Since I am a human, I feel the difference when touching the metal because I run at 98.6 degrees. This thing runs at roughly, let's say, 25 degrees Celsius. Actually, real quickly, humor me. You should probably know this. 98.6 in Celsius. Do it real quick.
Why does like 98.6 degrees feel hot?
Excellent question. We are built for the purpose of shedding that energy. So we are always, homeostasis I mentioned earlier, one of the main things that your body does is to run homeostasis, is to run cellular respiration, right? So to run the cellular respiration, it has to shed that extra heat somewhere. So you are your own, have you ever heard of what's known as a heat sink? Okay, a heat sink, we'll talk about these a lot in the next coming chapters, so it's a generic term, but let's talk about the heat sink on the back of your computer. The heat sink that's on the back of your computer is made of metal, and it just maximizes a surface area, and it's touching the computer. The idea being, it will be in thermal equilibrium with the computer, so if your computer, say, is at 110 degrees, the heat sink is at 110 degrees. What is the heat sink there for? It's touching the air around it, and the standard temperature of the room is 25 degrees Celsius, or let's go Fahrenheit. Let's say 70 degrees Fahrenheit. Automatically, what is that going to then do to the temperature of your computer? It's going to cool it down. A heat sink cools it off. You are your own heat sink. Your surface area out here is meant to lose heat all the time. You are radiating heat outwards always. We are heating up the room. One of the things, if you don't know this yet already, if they're like, why did it get so hot in this crowded room? We have like 20 heat. We have like 15 heaters in here. We have 15 heaters, all running at 98.6 degrees. What temperature are we trying to make the room be? 98.6 degrees, right? We are always heating up the room. AC, of course, has to continuously bring cool air in the room because you are always making the air hotter by being in the room, right? You are your own heat sink. So, what's then the problem, putting the question back to you, with if you run at 98.6 and you are now in a room with 98.6 degrees? There's nothing to cool you off. You have nothing to bleed the heat. So where does the extra heat go? Basically, it stays to you, and so you feel hotter in that particular instance. There's an interesting fact that like people always go, for example, I don't get it. In the desert, people always wear like a lot of clothes. They'll wear like these gigantic things. Well, why do you wear a lot of clothes in the winter? Be a little bit more specific. Agreed.
To keep the heat energy back inside.
because you're 98.6 degrees and are hotter than the outside, so you are trying to trap that heat energy. Why do you wear light clothes then in the summer? You want to let more of that heat out. Using that line of logic, why do they wear a lot of clothes in desert climates? They are colder than the outside. They are now, weirdly, at 98.6, their own AC relative to the potential 100 and 105 and 110 degree temperatures that are running outside. So literally wearing warm clothes in that, sorry, not warm clothes, my apologies, thick clothes in those areas insulates the cold in that particular case, bringing the temperature. It's weird, I know, to feel like it, but that's essentially what's going on. All right. How are we doing? Remember I told you this was an easier chapter. All right. So the interesting thing about thermal is that thermal is really at the heart of the entire conversation, energy. We didn't talk about this. We talked about, what did I give you as the heart of the energy? The equation that all energy is based around. What is it? Work. What's the definition of work? Force times displacement in the exact same direction. Simply put, if there's a force go that way, I go that way, work has been done. That's actually not at the heart of the definition. Okay? The heart of the definition is actually probably the calorie. Okay? The calorie, and this is, I believe, this is the lowercase calorie, not the uppercase calorie, meaning kilocalories are sadly absorbed into common culture, and they didn't want to say kilo a bunch of the time, so they just called it calorie, but every calorie you hear that they're talking about specifically out kind of eating food is in fact a kilocalorie. This is the standard normal one. What is calorie? This is exactly how much energy it takes to raise water 1 degree. By definition, energy is at the heart of thermodynamics. Okay? Simply put, I put this much energy in, put this much energy in, okay? 1 gram of water gets an extra amount of kinetic energy, right? It gets a more average. It gets a larger average. And here it is. It goes up 1 degree. It goes up that much average speed, that much average kinetic energy in that particular case. So again, notice that triple line right there. Triple line means we, scientists, physics, whatever you want to call us as a whole community, we decided that number, okay? And what it was. All right. Last conversation of the day. So what I mentioned a second ago between heat and temperature and internal energy, as always, comes down to a lot of like chemistry stuff and a lot of stuff, like simple stuff about metals. Metals wiggle around a whole bunch, and so they're going to be easier to heat. But what do we always do in physics? Whenever something gets very, very complicated and we don't want to try to describe all that crap and deal with all of that extra crap, we make a constant. We always make a constant. I'm going to ask this question a lot in here. When things get too complicated, physicists make a constant. We don't know what's going on. Somebody measure it and we'll call it a constant and move on. Meaning, we have defined little c as what's known as specific heat. Specific heat is Q. Q is actually defined as heat energy. That's the energy that comes from 2 things. So actually, let me go back to heat. When is heat going to occur? I've already talked about it generically, but let's make sure I hit this directly. More specifically, when 2 things touch that, that is true. What's that? Boom. If you're not the same temperature, you are transferring heat. So ideally, human beings run always shedding heat. Always, 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 always losing heat. Which is why, by the way, where does that energy come from? Food, or specifically you might have heard, we have given a generic name to it, homeostasis, this idea that if I'm just standing here, am I burning calories?
Yeah.
Yes, I'm using energy to run cellular respiration, and thus that cellular respiration goes out and bleeds that energy out in the form of heat, and I heat up the world around me, and blah, 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 and you know, that goes from there. But I will always bleed heat. Will my cup and this table bleed heat? More than likely not. Will my soda that came from the fridge probably about an hour ago, no, probably still yes. How do I know?
It's colder.
Colder. It is a colder temperature than the air. Now, this guy right here is still cold. If I had this much metal and I had it in the fridge, okay, and I had it in the fridge and I pulled out that much metal and set it here for an entire hour, do you think it would still be colder? Why not?
Heat outside transfers in.
Temperature metal has a lower specific heat, aka you can take less energy for the same amount of mass to change the exact same amount of temperature. So when you do this, this is its definition. This is how you're usually going to see it. I get heat by taking specific heat, which is the energy of joules over kilograms degrees Celsius, times what's the difference in temperature and how much mass is there. So in other words, if an object has way more mass, the same change in temperature, obviously it needs more heat. Okay? Or vice versa. If it has way more mass and I get the same change in heat, it's going to be less temperature change. Right? Here's an interesting conversation just real quick to end on. It's what's known as the Leidenfrost effect. People always talk about, like when they're talking about space and they're going to be irritated and not actually know any knowledge, they'll be like, I don't understand how there's astronauts up there. There's temperatures of like millions of degrees up there. Sure. Okay, absolutely there's temperature of millions of degrees. There are. But why is millions of degrees not really matter? Well, number one, is there very much gas up there? No. So even if those molecules have a large amount of temperature, aka average kinetic energy, is there very many molecules? No. So number one, they don't have a lot of internal energy. Great temperature, not that much energy in total. Also, what if I do the Leidenfrost effect is, let's say there is this giant amount of lava pouring down right here. Okay? It is entirely possible, if you do it right, to slap the lava with your bare hand and be completely fine. Why? Was there very much time for any exchange of energy whatsoever? So while it has a really high temperature, okay, slap the side of it, you're not touching it anymore, are you probably going to be fine? Yeah, you probably didn't change that much energy whatsoever. On the other hand, don't put your hand in a pot of boiling water because water has hydrogen bonding. So if you put your hand in a vat of boiling water and try to do that really quick, you're not going to get away with that because that water is still holding on to you and you're going to burn your hand very quickly. Plus the fact water also has steam, which has a huge amount of energy in it whatsoever. If you've ever been steam burned, you'll know this, but don't be burned by steam. It's a terrible idea. We'll discuss this a lot more on Tuesday. Test quiz Monday.
Well, I guess like it is, but like since there's not very many
Temperature is actually a terrible measure of space. It is. Because what temperature is space? Well, close to zero over here, and practically a million degrees over here by a separation of like 2 feet and wishy-washy. Plus the fact, as I just said, okay, why is that a million degrees space now, or if this is zero? How are they so far apart? There are like no molecules up there. So if I give any energy to the molecules up there at all, their change in temperature is going to be gigantic, like huge. But they don't carry that much total energy. They just move around much more on average because I gave them any amount of energy whatsoever. So it's kind of like, does an average describe a single person? No. So it's not perfect to say this, but imagine a single molecule floating through space. Does temperature describe a single molecule?
No.
Really doesn't make sense to do that. Temperature by definition is an average. An average by definition needs a really large amount. If there's not a large amount of molecules up there, it doesn't make sense really to use. I mean, we certainly do use it, but use it with the context, and then you get to these, these dumb idiots that, like I said, like they're talking about, like, well, NASA's not real. They said that there's like millions of degrees up in the stratosphere, and they walk around out there all the time. Yes, they have suits and tube, even if they didn't, you would be completely fine touching those millions of degrees because there's practically no total energy in that gas whatsoever.
See you next hour.
So we should just build like giant freezers that have heaters on them. No global warming.
Conservation of energy, Jeff. Where's that energy going to go? How do you get something to be cold? What are you gonna want?
I mean, like, we build heaters, right? And then put them in, like, freezers that insulate the hot air in there.
You already recognize why you're dumb and you're being silly, or are you like legit having this conversation?
No, wait.
Okay, I'm just trying to tell like what level I need to get on this. We'll discuss this more when we get to thermodynamics. Right now, I gotta take a class on Friday. What's up? Do one out?
Oh,
In the future.
Spain hours.
Never. Yes.
You stalled my lab mark is missing, by the way. You have my lab mark.
He does it every single week.
Thank you.
As soon as I possibly can. I have an overload right now with 2 AP Physics courses, and I'm trying to get caught up on them right now. And I've got no time because of a couple kids. I promise it. I also like early on wait a good amount of time until we have a good amount of assignments in there, so that we make sure, because if you don't do that, then one assignment jumps your grade a ton of time. So I apologize for that. I think I'm gonna try to have it. It should probably be, if not this weekend, early next week.
Okay.
Yeah. Yeah. Right.
Never mind.
Go back there. Don't go somewhere where you're gonna.
Oh, you're good.
Oh, my bad.
Yeah.
Oh, thank you. Alright, no, you just missed that. My mom asked me that. What? She mostly got it because of
That's over.